Hi, in this video we're going to cover Karnaugh Maps, or in most places or in other places you see them being referred to as K-maps. They mean the same thing. So this video is going to assume your knowledge of Boolean algebra, logic gates, and an OR gates, and use of truth tables. So that's going to all we're going to assume as we walk through how to solve Karnaugh Maps. Assuming you're already familiar with those things, then this video is going to be just what you need to understand how to solve Karnaugh maps. So very simply, a Karnaugh map or a K-map is a visual method used to simplify Boolean functions without having to use complex theorems or equation manipulations. So let's say we're dealing with a Boolean algebra expression and we've got something funny that looks like AB not C or A not B or not A not or not A not C. Okay, so this is Boolean. This is an Boolean algebraic expression. So you've got A, B, and C. So it's Boolean algebra because we're dealing with a Boolean variable, a Boolean. So one of them is A, and A can either be 0 or 1. So that's false or true. So that's what makes it Boolean algebra. That's what makes it Boolean logic. So if you have a Boolean expression like this, the natural algebraic way you go about solving it is trying to convert this to some sort of standard SOP, sum of products method, which will involve multiplying with, let's say for instance, so you have A, let's write this more clearly. So you have AB not C, or A not B, you may choose to multiply with C or 1, or not A, C, B or 1, which already from the get-go makes this a bit more complex than it already is. So we have to do with expansion to ensure it goes from non-standard SOP to standard SOP, all the way through and forth, back and forth with simplification and factorization, trying to get the simplest, most reduced form of this expression. But what happens with Karnaugh maps is that it now becomes a visual method and not really an abstract mathematical way of doing it. Truth tables are accurate because usually the way you do this, you have truth tables listing your variables and some sort of 0 0 1 0 0 1 to try and sort of get your output line. Okay, what each combination of input gives you at the output. But how Karnaugh maps, they're accurate, but once the variables increase, simplification gets rather painful. Karnaugh maps or K-maps turn Boolean simplification into an entirely visual pattern problem, which is much more appealing, a better way to solve it. Before we go, however, there are some things that I have to ensure are crystal clear before we continue. The first one is bit flips and gray code. They're actually together. So let's say we want to write the binary numbers from, okay, so let's say 0 1 2 3 4. So that should be 0 0 0 0 0 1 0 1 0 0 1 1 and 1 0 0. Okay, so this is decimal, so let's say this, and this is binary. And this is perfectly fine. This is an exact mapping of a decimal number to a binary number. But if you watch as you move from one number to the next, okay, so let's take for instance as we move from 1 to 2 in binary, we initially have 0 0 1, and we plan on moving to 2, which is 0 1 0. There are 3 bits here, so that's 1 2 3, and there are equally 3 bits here, 1 2 and 3. So 1 changes to 0, so that's 1 bit flip. 0 changes to 1, that's another bit flip. So in binary, going from 1 to 2 is 2 bit flips. Does that kind of makes sense now? And you see it even gets more. Let's say we're going from 3 to 4. So 3 is 0 1 1 and 4 is 1 0 0. So if we were to map this flip, so this is 1 because 1 changes to 0. This is 1 because 1 changes to 0. And this is 1 because 0 changes to 1. So this is 3 bit flips, which doesn't pose a problem if you really don't have much to do with binary. But in Karnaugh Maps, this is a very big problem because we need to make sure that our numbers, moving from one number to another, incurs only one bit flip, which is why we use what we call gray code when dealing with binary, when dealing with Karnaugh Maps. Okay, so the entire purpose of that is to decimal gray code. So let's say we've got 0, 1, 2, 3, and 4. So 0 is going to be, usually 0. 1 is going to be 0, 1. 2 is going to be 0, 1, 1. 3 is going to be 0, 1, 0. And 4 is going to be 1, 1, 0. So as if you inspect, you see going from 0 to 1 is 1 bit flip, since this is the only one changing. Going from 1 to 2 is 1 bit flip because 1 stays constant, 0 stays constant, and we have a 0 flip into a 1. Going from 2 to 3 is still 1 bit flip because the first two bits stay constant. This changes to 0. And then going from 3 to 4 is equally still 1 bit flip because the last two stay the same and 0 changes to 1. So that is the purpose of gray code. So when dealing with Karnaugh Maps, we won't list binary numbers the way we're used to. We'll have to use gray code because this bit flip, ensuring we have a maximum of 1 flip when going from one number to another, is going to prove very important as we carry on in solving problems. The second one is adjacency. Adjacency. Okay, so I'm just going to fill up this Karnaugh map so we kind of get an idea of what I mean when I'm talking about adjacency. Okay, so let me use this as 1, leave this as 1, and make these guys 1, and fill the rest as 0. Okay, so adjacency, as you would usually mean in English, is things that are beside each other. Okay, in Karnaugh Maps, so this is a K map. In Karnaugh Maps, it is important that we're able to identify which these are called prime implicants. Okay, so let's get that out of the way. Prime implicants. So prime implicants happens when you have a group of ones in a Karnaugh map. But don't worry, as we solve problems, you see the use of this. So if we have a group of a random arrangement of ones, we need to find out what makes these guys adjacent. So Karnaugh maps have very specific rules to play by. Okay, meaning that these guys are adjacent. These guys are adjacent. So these two grids are adjacent. These two grids are equally adjacent. These two grids are adjacent. And all 4 of these grids are adjacent with each other. So if, for instance, all these were 1, then it would be very fair to assume that, okay, these 4 are all adjacent to each other. But then here's where it gets really, really funny. This guy is also adjacent with this guy. Okay, so it's more like a cylinder. Karnaugh maps wrap around the edges to ensure adjacency. Alright, so how are we able to tell? So if we were to identify this box, okay, with ABCD, so this box over here is going to be, so our AB column is 0, 2 zeros, and this is 1, 1. And then this box over here is, this cell over here is 1, 0, so that's A then B, 1, 0, and then our columns are 1, 1. So you try to count the bit flip from this to this. Here we have 1, 0, 1, 1, and here we have 0, 0, 1, 1. And you can see that it's only the first bit that is changing, meaning that we've shown that these guys are adjacent to each other. The same thing applies for this and this. Okay, so this is 1, 0, 1, 0, and this is going to be 1, 0, 0, 0. So you can see the only blitz flip is happening in the third from the left. So Karnaugh maps are adjacent around the edges and around the tops. So these guys, so this box as it is this way is adjacent to this box as it is this way. Cool. So that's one of the more important things about Karnaugh maps. As you get to solve problems, it will become more natural and less spooky. So let's get right down to business. So we have a truth table, okay? So this is a truth table. It's a two input truth table since we've got A and B. And what we're going to try and do now is draw the Karnaugh map expression for this. Okay? So we've got two variables, so we're going to have a nicely done table. Okay. 1, 2, 3. 1, 2, 3. Yeah, this looks nicely done. Okay. So let's let this bottom sign represent A and this for B. So we've got 0, 1, 0, 1. Okay. So the same way we had 4 outputs on our truth table, 1, 2, 3, 4. We also have 4 valid cells for our truth table here. 1, 2, 3, 4. To map the zeros and ones of the Karnaugh map. Okay, so let's do that. So 0, 0 gives us 1. 0 on A and 1 on B gives us 0. 1 on A and 0 on B, so that's this, gives us 1. And 1 on 1 to 1 gives us 1 also. So there you have it. You've drawn our first Karnaugh map. So as we said, the entire purpose of this is to be able to find adjacencies, okay? The number of prime implicants. So this is pretty simple. So we know that for every prime implicant, we want each box, because we're going to draw a sort of box. It may be rectangular. So let's say 4 by 1, 4 elements, or it may be square. Ooh, that's not a square. Or it can be a single cell. But the point is that each prime implicant, each set should have a value which is an exponent of 2. So it could have 1, it could have 2, it could have 4, it could have 8. Okay, growing in that manner. So as we solve more problems, we see that being applied. So we can see that this is one prime implicant, and this is another prime implicant. Okay, so for this particular truth table, we have 2 groups, 2 implicants we're looking at. So the next thing we're now going to look at is we'll pick each one. We pick each group of ones we've highlighted and try to say, oh, which Boolean expression, which Boolean combination is valid for this implicant set I've chosen, because it's going to be in values of 2, right? So let's look at this first one we picked. So it goes this way, and then we see that this cuts across both A being 0 and A being 1. So this doesn't depend on the value of A. So here you have B, and here you have not B. So the entire value of the output on this truth table is in not B, but it cuts across both A. But it cuts across both A and not A. So we know that the variable for this first one doesn't depend on A. So we can write for this first group, our output is going to be, so we can say, okay, let me say X. X is equal to not B. For this first set, we're just able to do that. If we get over to the second one, okay, we call this is the second. Okay, we did this before, but this is the second implicant set we've chosen. So we can apply the same logic. This prime implicant set cuts across both B and not B. So the output doesn't depend on the value of B. However, all of them are all on A. So we know that this is OR A. So the way this works is that it's more like a sum of products. For each implicant is going to be an expression, and then you're going to OR it. Okay, so now we know that the most simple form of expressing this is x is equal to a or not b, which really shows that Karnaugh maps are really sort of fun way to approach dealing with binary logic. So let's look at one more problem before we call it a day. Okay, so we still have two variables. So we're looking at x as our output. We'll draw our Karnaugh map. Okay, and go this way. 1, 2, 3, 4. Okay. So let's call this A and we'll call this B. So 0, 1, 0, 1. So if it does help, you can just sort of point out that this is the region where A is, asserted, where A is positive, and this is where B is positive, just kind of by the side, so that you keep it at the back of your mind. So once we do this is drawing our Karnaugh map. Drawing our Karnaugh map. Okay. So once we're able to draw a Karnaugh map, next is to map from the truth table. To map from the truth table to the Karnaugh map, so that we can be able to find the prime applicants. Okay. So 0 on A, 0 on B. So that's not A not B, gives us 0. So not A and B gives us 1. So that's not A. Not A, not B. So not A and B gives us 1. Not A and B gives us 1. A and not B gives us 0. So A and not B. And A and B give 1. Okay. So now, recall what we said. We're looking to find the group of prime implicants. Okay. How can we group the number of ones in such a rectangle, in such a square, that each one has 1, 2, 4, or 8 members? And we can sort of see already that this is pretty simple for us, since these guys fall in a nice pretty rectangle. So we don't even have to particularly do much. This is nicely done. So recall, the next step is now to find, hey, we have one set of prime implicants. What Boolean expression defines this set we've just picked? So we can see that this cuts across both A and not A, so it doesn't depend on A, and it's found entirely in the region of B. So we can boldly, confidently say that X is equal to B. And when you do look at it, you find that if you delete the entire A column, your output X matches B exactly, which you may not have easily found out if you were trying to, do some sort of Boolean algebra manipulative way. Okay, so that's the entire point of Karnaugh maps. They provide a simple visual way for us to look at a truth table, look at a complex expression, point out the reduced form, the lowest possible form of that problem. So we'll solve more problems in the videos coming on. We're going to 3 variables with some more complex problem sets, and I'll see you on the next video.